yeah, with this, I'll introduce our invited speaker. So thank you very much, John, to accept being here. And this talk is going to be about make tree to throw away frontiers in homotopical proof assistance. So I'm very excited to hear more. Yeah. So
great. Thank you very much for the warm welcome. Yeah, I'm very honored to have been invited to speak to this great meeting. I want to thank Jesper and Richard for working so hard to make this event happen. This is a really good moment for our community to have such a meeting. Also want to thank the student volunteers and also all the attendees.
1 second, it seems that the room can't hear you. So I'm sorry. They're having a problem with the audio again, unfortunately. Let's not jinx it. But,
yeah.
Oh no! All my nightmares about
yeah.
the hybrid workshop. Yeah.
Yeah.
So. Been practicing how to do online conferences for 2 years, and now it's the hybrid conference to make things more difficult than when we finally figured out how to do online conferences.
Yeah. Well, hopefully this is the last hybrid one that you'll have to do.
I hope so. Yes, I hope this will not become. Well, yeah. I mean,
maybe we'll just get really good at it, so that could be okay.
That's also acceptable, I guess.
Yeah.
I mean, it has some advantages, but yeah.
Yeah.
It has to work, right? Yes. Indeed. So in two more years, we'll have to forgotten how to do in-person conferences.
No, we can hear you now. We're back. I think.
Oh.
Great. Then yeah, please continue then. Yeah.
Okay. Carry on. Thank you.
All right. I'll just start from the beginning because I only said 10 seconds worth of stuff anyway. So this talk is called Make Tree to Throw Away, Frontiers in Homotopical Proof Assistance. I'd like to thank Jesper and Richard for all the hard work that they have done to put this on, especially considering the difficulties that are obvious to everyone of putting on a hybrid event with technical capabilities. Thanks also to the student volunteers, the program committee, and everyone who has come together to make this happen. I hope that everyone is having fun, and I'm really looking forward to hearing the rest of the talks. So I want to tell you a little bit about what we've been doing on in the RedPro development team. And so just to say, this work is the work of my comrades, Carlo and Julie, Evan Cavallo, Favonia, Bob Harper, and Reed Mullenix. And I'm going to give you my own personal take on it, but all the stuff that has been done has been done not just by me, but by all of these great collaborators. So as a team building proof assistance, Our work is a little bit different from some of the other first-class tools that are represented here at this workshop. We have not been trying to build big production quality tools. If you want to build a big tool and like have it actually work well and be usable to prove significant results, you need a lot of money, and you also need a lot of people working on it who do not need to have an academic career. Oh my gosh, they've lost the audio again. Okay.
Oh no.
Well, I wish I knew how to give sign language or something.
Yeah.
I guess I have my slides.
Or just open a text editor or something and write out all your...
Then you'll get to see how bad my typing skills are.
No, this is... I think everything is also being streamed to YouTube, so yeah, it's going to be an interesting YouTube video unless they do some...
So they're going to be like, what on earth happened here?
Yeah.
Okay, hello again.
Great.
All right. All right. I'll just resume, and please tell me to stop if you lose me. So building a big, like a production quality tool is a really big endeavor, and a lot of the work that you have to do to make that happen is work that basically will prevent you from getting a professorship or from getting tenure as a professor. So for us, we have had to define success as coming up with good ideas that will get incorporated into the next generation of big tools that can be built by people who are equipped to build them. And so the RedPro project, in which we have built 3 different proof assistants, we have been trying to build small prototypes that exercise a particular idea as we search for what the right way to build interactive proof assistants for higher dimensional type theory is. And so there's that saying, like, build one to throw away, I think maybe from the Mythical Man Month or something. And we built 3 to throw away. So why are we building proof assistants for higher dimensional type theory? What's the point? Well, we view ourselves as coming from this tradition started by Per Martin-Löf that begins with the identification, a profound identification between mathematics and computer programming. But the rub is that Martin-Löf's type theory is not a language in which you can actually do almost any basic mathematics. And I want to emphasize that it was never meant to be a language in which you could do that. Martin-Löf type theory in its modern incarnation is the bottom half of a 2-layer foundation. The top layer could be something like sectoids or some other more sophisticated type theory in which you can develop mathematics. And the bottom layer was meant to be this very simple intentional type theory. And that can be one way to address the difficulty of putting math into type theory. Higher dimensional types have arisen in the past few decades as a different and alternative approach that is monolithic, has just 1 layer, and it has a number of advantages. So I want to point out several important things that any type theory that you want to be able to use to actually do math needs to have. And these basically pertain to things like functions and propositions being well behaved. The first 2 properties, function extensionality and function comprehension, basically mean the following. It means functions are exactly the same thing as their graphs or functional relations. Function extensionality is one direction of that equivalence, and function comprehension, which is sometimes called the axiom of unique choice, is the other direction of that equivalence. Now, people like to say, oh, graph equals function. That's a principle of classical math, not constructive math. This is actually constructive. It's just that in some kinds of constructive math, it doesn't turn out to be true. But in the constructive math that you can use to actually do stuff, it's true. Propositional extensionality is a similar relationship. It says that types that have at most 1 element if you have an isomorphism class of those types, there's exactly one proposition that encodes that type. And this has profound consequences, including quotients that work properly. That is, if you have you can take a type in an equivalence relation and quotient it by that equivalence relation, something that happens all the time. But what happens if you take two arbitrary elements of the original type, you put them in the quotient, and then they become equal? Does that mean that they were in the equivalence relation that you started with? It does if the equivalence relations are what's called effective. And that's a property that is, again, needed to get any math off the ground. None of this stuff works in type theory directly, but you can solve it in a variety of ways. Setoids are one way to solve the problem, and higher dimensional types are another way to solve it. The crux of this higher dimensional approach to type theory is this principle that was introduced by the late, great Vladimir Vygotsky called univalence. And just like the elimination rule for the identity type in type theory says that if you're trying to prove something about all identifications between elements of a type, it suffices to prove it only about reflexive identifications, that is the trivial REFL term, like in AGDA. So univalence says if you're trying to prove something about all isomorphisms between types, it suffices to consider just the ones that are tracked by the identity map. So this principle sounds like it's pretty simple, but when you add it to type theory, a bunch of important semantic things, like the things I mentioned before, suddenly become true. And the problem is that when you add it to type theory, a bunch of other good things about type theory are no longer true, like the fact that you can run terms in type theory as if they were programs. And so cubicle type theory has been a long-term project to address this problem. So the idea of rebuilding type theory in a cubicle manner, which I'll briefly describe, was proposed by Coquin to give a version of univalence that actually you can run like a program. And there's been a lot of work that I don't have time to describe, but it's been a very successful project in my view. And the basic idea of cubicle type theory, which is the theory that we have been implementing in our tools in the RedPro development team, is to add something to modern lift type theory. You're adding a new sort called the interval, whose elements are called dimensions. And we're going to add two constants, 0 and 1, but there's not going to be any case analysis or recursion principles. So it's kind of like an abstract type in a programming language. And then we're going to have a universe, a special universe of proof irrelevant propositions. So it's sort of like a fragment of S-prop, if people are familiar with that in Coq. And it's going to have some closure conditions. So it's going to be closed under equality propositions just for the interval. And these equality propositions are going to have equality reflection. It's going to be closed under finite conjunction and disjunction of these propositions. And the disjunction needs to have a case principle that you can eliminate into any kind of thing in the type theory. And it'll have some quantifier. And the point of all this machinery is that we can get a new way to define equality or identification in type theory as a kind of function space. If you want to talk about a proof that two elements of type A are equal or the same somehow, you can make a function from the interval into A that when you apply it to the constant 0, it returns the one thing. And when you apply it to the constant 1, it returns the other thing. And because there's no case analysis principle, you don't always have such a function. And the beauty of this notion of identification in type theory is that as a function space, it commutes with all the other function spaces. And that means that there is a definitional isomorphism between the collection of proofs that two functions are pointwise equal and the collection of proofs that those functions are equal. So we have a very strong form of function extensionality in type theory. So this is really nice. And so that's what we have been trying to build with cubicle type theory. And over the past several years, there's been a lot of implementations of cubicle type theory, going all the way back to the beginning with Simon Huber's evaluator. It was not even an implementation of cubicle type theory per se, but rather a program that would run a cubicle term and give you an answer. And then this has gone all the way to the present day, where there are actual interactive proof assistants like the excellent Cubicle Agda tool, as well as two tools that my team is responsible for, RedTT and CoolTT, and also some tools that are maybe from a bit outside the center of this community, but also deserve our attention, like the mlang project on GitHub. So I want to, there's a lot to say here, and I can't talk about all this stuff, so I'm just going to talk about what we did. But I need you to place that in the context of a lot of people have been working on this, doing a lot of really excellent work. So I'm going to tell you the story of our projects, RedPro, RedTT, and CoolTT. And then I'm going to give you some of my thoughts on the future of interactive proof, and especially this community that we're building here. So RedPro was a project that I started, well, slightly before I began my PhD at Carnegie Mellon. Just to give you a picture of the perhaps irrational and excessive exuberance and bombast with which I initiated this project. I have to say, I think the Coq team won this battle because I'm a pretty heavy user of Coq today. But I have to say that is how it started. RedPro, the idea of RedPro was basically to take Nuprl, which was one of the first proof assistants for dependent type theory, and make it higher dimensional. That was roughly the idea. And there's a lot of confusion in the community about what Nuprl actually is. So I want to set the record straight and clarify what the idea was. Nuprl is basically the idea of using types to impose structure on untyped programs. In Nuprl, there's actually a type of untyped programs. And then there's another type that witnesses the fact that some untyped program has a particular type. So well-typedness is not a fact that comes with a piece of code. It's actually a theorem that you prove about a piece of code. As a technical matter, you don't have judgmental equality. You have only propositional equality in Nuprl. But there's a very strong elimination rule that is equivalent to having equality reflection if you were to present the theory using judgmental equality. And the way that you use Nuprl is you're not constructing proof terms. Instead, you're writing an untyped program, and then you're proving in the logic that the untyped program is well-typed. And so you're constructing a typing derivation using some tactic language like LCF. There are untyped computation rules that allow you to, in some cases, adjust a goal by maybe doing some reduction or something. And maybe a point that is worth making is that even though Nuprl has the equivalent to equality reflection, you still have to manually apply that. And in fact, things like eta laws are not automatic in Nuprl. Anything that goes beyond alpha equivalence of terms, that is renaming of bound variables, you actually have to manually apply using a tactic. And this tactic is going to induce some additional subgoals every time you use it. So I really want to clarify that if you're comparing, say, Nuprl to Agda, Nuprl has automatic alpha equivalence. Agda has automatic beta eta equivalence. So RedPro was Nuprl plus cubes plus univalence plus higher inductive types. That was the idea. And this is a screenshot of what it looked like to write some lemma in RedPro. So many people are aware that RedPro, even though it is in the name of our team, is not what we're building today. And I think that we have not been fully explicit about why we changed direction. And I think that today is a wonderful time to share our experience with the community. So at the time when I started this project, I strongly believed in a number of hypotheses that now I no longer believe in. So the first one was that decidable type systems validate too few equations to be viable. That's something I believe. And the reason I believe that is that, well, in math, you need a lot more than beta eta. So what are you going to do? Like I just alluded to, for me, what we found is that it matters a lot which equations are automatic and which ones are not automatic. Beyond the automatic equations, the ones that the machine takes care of for you, you definitely need a lot more equations. There's no denying that. But among the automatic ones, if you can get all of beta and eta laws, that's really great. If you can only get alpha equivalence, that's not so great. The next one was that type checking, even if it's decidable, is infeasible in practice. It is true that if you you can prove complexity theoretic results that show that type checking is basically a bad problem, has awful complexity. But that's very different from what happens in the usual case when you actually use it. The reality is that Thierry Coquin's 1996 type checking algorithm is blindingly fast in the usual case. And some recent work by Andras Kovac has shown that there's also a lot of room for optimization. So I think this is an excellent direction, and it shows that type checking, even very rich programming languages, is practical. The next thing was that we thought that we could simulate type checking for simple programs using a heuristic tactic in our system. And our motivation for this was, well, it's in a decidable type system, you could have something run for 1 million years and it might terminate, but who cares? Because as they say, it's like running after undead is no different from running forever. But this is actually very sensitive to the global properties of the formal system that you're looking at. For instance, if it is the case that your system admits long inversion phases during proof search, then a tactical heuristic can be a good option, even in the absence of decidable type checking. Unfortunately, for Nuprl and RedPro, almost all the rules are totally non-deterministic, and there are no inversion phases. So Andromeda, a system that has equality reflection, is an example of something that I think this approach could work for. And there's been some really interesting recent work by Anja Petrovic and Philip Haselwater and Andre Bauer on that approach. But it doesn't work for Nuprl and RedPro. And to say a little bit more about equality reflection, well, what I thought would happen when I added equality reflection. So my expectation was that, okay, I'm going to have some insanely hard proof goal, and I'm going to just obliterate it using equality reflection, and I'm going to stop getting owned by all this EQ, RecT stuff in Coq, and it's going to be great. But what actually happens is that you need to use equality reflection every time your goal is off by an eta law. But the eta, the thing that is off by an eta law might be very deep in a very big term. And so when you want to rewrite by that, you actually have to prove an additional goal that shows that that your goal is a function of that hole in the term where you want to do the rewrite. And this is often very hard to prove. So that's basically a non-starter. So that took us back to the drawing board. So after this experience, we began to design the RedTT proof assistant. And I guess some propaganda art that I drew at the time. This is a picture of what some code looks like in RedTT. But suffice it to say that our experience with RedPro won us back to the European orthodoxy, and particularly these ideas, which I think can be located in Sweden, mainly. This normalization by evaluation, bidirectional type checking. And also a very important principle, which I guess doesn't come from Sweden, but I learned from Connor McBride's thesis, which is that proof states should always be well typed. This is a really important property that I think is under recognized. So I want to say a little bit about a few of the things that are interesting in RedTT. The first is that I mentioned that for cubicle type theory, we impose an equality reflection law for the proposition that two dimensions are equal. But I just got done telling you how much equality reflection blows. So why is this okay? Why doesn't this break implementation? Here's why. So we have very carefully stratified RedTT's type theory such that there is a cubicle layer that contains things like the interval and these special propositions and all of that stuff. And then on top of that, there's type theory. And there is some interaction between these layers, but it only goes in one direction. The cubicle stuff does not depend on the type theory stuff. As a result, because the theory of the interval is decidable, you can you have no problem when you add type theory to that. It remains decidable because there is this strict phase distinction between the two layers. If you allow these things to get mixed up, then your type checking algorithm will no longer be complete. It's very easy to a type checking problem that is actually equivalent to the halting problem. And so what happens in systems that do not stratify, such as cubicle AGDA, is that if the user stays within the stratified fragment, everything works right. And if you go outside the stratified fragment, some unexpected things may happen. So I want to emphasize that this phase distinction is actually really important. Now I want to come back to some great ideas that I learned from studying Conor McBride's work, which thinking about this carefully led to another important contribution of RedTT in my mind. The first is this, what I call McBride doctrine. I don't know if Conor would like me to call it that, but the idea for me is that the role of the machine is to assist human beings through the intermediate steps of a proof act. Interactive proof is much more about the middle of a proof than the end of the proof. And in my belief, there are 3 rules of discipline, so to speak, that if we follow them, we will be facilitated to achieve compliance with Conor's doctrine. The first is that when you're decomposing goals into sub-goals, like when you in elaboration, or when you have a constructor in your language, you have to decompose them into sub-goals that jointly entail the main goal, subject to no side conditions. So the no side conditions thing is the important part. The other part is obvious. But if you add side conditions, you immediately start to disrupt interactive proof. And I'll show you how that happens. The next thing is never spawn a sub-goal whose statement is not well typed. Even if you've got another sub-goal in flight, which when that one gets proved, this one will become well typed, don't do it. It's not going to work well. And then the last principle, which Conor calls bidirectionalism, is that information should be flowing inward from the goal and outward from the context. This facilitates elimination of redundant information, redundant proof nodes, and it makes for really user-friendly systems. So we're actually violating these rules of discipline all the time. The way it most frequently happens for me is that, let's say I'm doing something in AGDA, well, what will happen is that for 58 minutes of my project, almost my whole buffer is yellow. And for those of you who haven't used AGDA before, what yellow means is bad. It means that your code doesn't have any meaning. It means that it will have meaning if AGDA manages to solve some deferred unification problem. But right now, it's just ASCII. So I understand why that happens, but I also understand that it disrupts the interactive flow of the proof. But this can also happen in Coq, although it happens less often now than it used to in my experience, which is that you do some big proof in the tactics, and then you hit QED, and then something goes wrong, and you don't know what. Sometimes this will happen if there's a bug in the universe level polymorphism. It doesn't happen so often anymore, but this is just an example. So we have seen that this McBride principle is challenged by the heavy use of unification in modern tools, but cubicle type theory actually makes things way worse in this respect. Introduces even newer problems that challenge this principle. So here's the example, okay? Let's say that you're trying to make a path or an identification between 2 elements of dependent sum type. So we start off with a hole, and we're going to use the introduction rule to the path type, which says that we're going to make a function from the interval into the dependent sum type. And this function has the property that if you apply it to 0, it becomes u, and if you apply it to 1, it becomes v. Okay, that's good. And we've got a hole over here now, and it's a hole in one variable. Well, here's the problem. This hole is just a fresh meta variable. It is a totally generic term that satisfies no properties whatsoever except the ones demanded by its type. And so in particular, it does not satisfy either of these 2 properties. These are these side conditions I was warning you about. So that's not good. But let's say that we make our system so that it defers that constraint until later. So instead of being red, we'll let them be yellow. Okay, that's good. It's working. Now let's apply the introduction rule to the dependent sum type. We've split our hole into 2 holes. We've got to make an element of A and an element of B. Now we still have these side conditions over here, but now they're kind of delocalized from our goal. If you're just looking at the goal A, what do I got to do to make an A such that this condition holds? What's going on there? So the problem is that we've got these side conditions that are now completely taken away from their context. So we're going to just try to finish the rest of the program and hope it's okay. And if it works, the yellow will turn to white. And if it doesn't work, the yellow will turn to red. And we'll get an angry error message. So this is indeed proof, but it's not interactive proof. So in RedTT, we solve this problem, at least for types that have eta laws, in a different way. Instead, the judgments of RedTT are annotated with a partial element. So phi is some condition on the interval, like I equals 1 or something like that. And W is an element of the path type that is that we're trying to construct an element that is equal to W when phi is true. So that's what we're trying to do. And all of the rules of type theory in here will then decompose these conditions into smaller conditions. So here's how it works. If we apply the introduction rule to the path type, we're going to have a hole in one variable, no side conditions, but we've extended this partial element here. So now, in addition, so because we're trying to make an element of the interior of the path, this dependent sum, we want it to be equal to W under phi. That is, we want it to be equal to W applied to I under phi. But now we have additional conditions. We want when I is 0, this thing needs to turn into U, and when I is 1, this thing needs to turn into V. So there's still no side condition. This is actually the goal. And we can apply the introduction rule for the dependent sum type, and it will decompose further. So now we're going to have to make an element of A and an element of, oh, this should say B over here, not A. And what's going to happen is that we're going to take the this partial element that we had for the dependent sum, and we're going to apply the first projection to it on the left and the second projection to it on the right. So now the conditions that pertain to the main goal have been completely localized to the sub-goals. So this is an important part of RedTT's usability. And notice there's never any parts of this theorem-proving process that turned yellow. And so I want to say that Connor McBride has also been pushing a similar idea. And we're really happy to see that this interface, this user interface was added to Cubicle Agda in November 2019. So thanks to Andrea Vezzosi for doing that. It's really nice. It's really nice to use that in Agda. So the next thing that we built after learning what we wanted to learn from RedTT is CoolTT, and we're still working on it. So here's a picture of CoolTT. By the way, don't ask me about the name. I don't really know why I call it that. Some people thought it was a pun on homotopy type theory because that's hot. I just did it because I like the sunglasses emoji. So CoolTT is very similar to RedTT. Most of the changes are under the hood, but they're pretty cool, so to speak. CoolTT is based on a logical framework presentation of cubicle type theory. So we have this outer cubicle layer, and then we build cubicle type theory as a universe inside that outer logical framework. We have a new and more efficient evaluator for cubicle compositions and coercions, which are these notoriously painful parts of the cubicle algorithm. And something that we're quite proud of is that we have, so I mentioned that you have those disjunctions of propositions, these cubicle propositions, and they need to have case split principles that apply not only when you're trying to prove another proposition, but also when you're trying to prove an element of any type, or even to construct a type itself. And these are very hard to implement properly. But we have implemented these in such a way that they have the full eta law that one would expect for a push out, which is what these are semantically. And you can use them in any position whatsoever. So this gives rise to a theory that is complete for this disjunction language. And the completeness actually depends entirely on the stratification that we introduced in RedTT. We also have some really nice subtyping principles. So RedTT had these very naive subtyping principles where it's like real subtyping, like something is an element of one type and it's also an element of another type. In CoolTT, we have a fully typed representation, and so subtyping is really coercions, and coercions are guided by the eta laws. This method works so well that you can have, say, something that looks like the identity function get easily elaborated to something that has this very complex type. that turns a dependent sum into a non-dependent sum, but with subtypes on the inside. So this is something that is really, really nice to have. So something that we're thinking about a bit more is nowadays is building immersive experiences for people who are trying to construct higher dimensional terms. Because it's really hard to construct higher dimensional terms. And this one, we decided not to implement this version. This is basically what we want to implement, but we don't know how to do it yet, but we're trying. But we do have a working prototype where you can type some magic word into a hole, and then all of a sudden this really cool window comes up that shows a spinning cube that you can actually move around with your mouse, and it will show the boundary. Remember I said that these cubicle holes have these partial elements. It'll draw that partial element on a cube of any finite dimension, and you can interact with it using your mouse. It's really, really, really cool. So this is something that our colleague Reed Mullenix has been working on, and I love it. Obviously, it's pretty rudimentary right now, but we definitely, I think this is a great direction to go. So I want to zoom out. That's about all I want to say about the specifics of this, of our story in the RedPro development team. And I want to talk more about the community of people doing interactive theorem proving, especially of the type theoretic variety. This community is paradoxically very, very small, but it's also very fragmented. And I think this goes back to like a cultural sin that was committed all the way back maybe at the very beginning of interactive proof. And I think it's time for us to grow up. It's not time for us to start all working on the same thing. I think it's really good that we have Coq and we have Agda and we have Lean and we have all these smaller projects like the ones that we've built, but also the ones that cool people on GitHub are building. So I'm not saying that we should all work on the same project, but we do need to do a better job of being connected to each other and understanding what each other is doing, and because there's a lot to learn from each other's experiences. And so I think it's time to unite, and that's why I'm so excited about WITS, because I think this is a really great step in that direction. And I think in the spirit of uniting, here are 4 ideas that I think that we can unite around and sort of treat as things that are consolidated and things that we believe. The first is that the semantic type checking algorithms in the style of Andreas Abel and Thierry Cocon and normalization by evaluation are both fast and practical. It really works. And the recent work of Andres Kovac, which is amazing, has shown that it can be really, really, really fast. In the past, there were a lot of good reasons to be concerned about having ELAs and about unit types and so on, but I think the past is the past. Next, interactive theorem proving is about the middle of the proof, not the end. I don't even care if it works at the end. All I want is for it to work in the middle, because I'm using this thing as an augmented brain. That's what I'm using it for. So down with the yellow code, uphold the 3 points of discipline. Next, we need to have a smooth handling of algebraic hierarchies. This is the biggest reason, in my opinion, why people are not using our tools to do actual math. It's because it's really, really hard to do it. I think experience has shown that the SS Reflect style of algebraic hierarchies works really, really well. And it's nice to see that it's being reified in this hierarchy builder tool that some people are working on and have presented last year. This stuff is very subtle to get right, and I think it needs language level support. And there's some nice ideas in the RN proof assistant for doing that as well. I think that this is something that we need to pay attention to and not treat as an afterthought anymore. And finally, this is an old idea, but I think it has been controversial for a long time. And today, I think it shouldn't be controversial. Total type theory is great, and it works for general purpose programming. Lean 4 and Idris 2 are wonderful examples of where you can create programs that do all the things that normal people think that programs are supposed to do, but you're doing it in a dependent type theory. Oh, I wrote Iris. I meant Idris. I'm sorry. Yeah, sorry to the Iris team. But basically, I want to say that I think that this stuff is great and we should be using it and teaching people how to use it. For people working on higher dimensional types, we've got a number of challenges ahead of us. The first challenge is that the homotopy coherence is a thing that is really, really semantically well behaved. It's fantastic. Homotopy coherence basically means that rather than asking for everything to be equal, you ask for two things to be equal up to another identification, and any two of those identifications to be equal up to another, and so on. But homotopy coherence is way harder to use than proof of relevance. So how can we build interfaces to this great semantic idea that are easy to use for normal people? Another thing that is perhaps lesser known is that this distinction between two ways to think about higher dimensional structure. One is lifting, and that's all this cubicle and simplicial stuff. And the other is pasting, which is the idea that you can draw some higher dimensional picture and just glue it onto some other picture and you get a bigger picture. And the pasting approach is well represented in a really cool tool called Homotopy.io that's being developed by the team at Cambridge. Anyway, I think that we should try and understand the relationship between these things and see if we can come to some kind of unity in our tools that gets the best of both worlds. Zooming out from that, we need to develop visual tools because these things are way too hard to visualize if you just have some really big expression in type theory. So having a tool that allows us to pass back and forth between symbolic and geometrical would be really important in my opinion. And then finally, the elephant in the room is that cubicle computation is kind of hypothetical in the sense that yes, we can compute, but we don't know how to compute without substitution compared to ordinary type theory where we just know how to use an environment machine right away and it's fine. Cubicle things are harder, and we need to figure that out before we can tell people that you should use cubicle type theory to write your next web server. Some challenges for our community in the broader sense. We need to be applying our tools to real math, and so that's why I've been really excited to watch the Lean community, especially the MathLib project, and see what they're doing. It makes sense that most of us, our applications for these tools would be, we have to do 1,000 case induction for a POPL paper. But having a tool that's really good at 1,000 case inductions does not mean that it's any good at all at doing abstract math. So 1,000 case inductions are great, but we need to have something that can do abstract math. This is really important. On a more somber note, I have seen that the blockchain and related trends are currently a very hot area of applications and funding. But I think the short-term funding of interactive theorem provers is not worth destroying our living environment. A community needs to respond quickly and resolutely against this menace to the human life form. On a lighter note, we have a lot to learn from hobbyists. I see a lot of people saying, you know, in the POPL community saying things like, oh, dependent type theory is the hardest thing in the world. You have to be a wizard or a genius, a cubicle is impossible. But the Zoomers are taking a break from TikTok to write their own implementations of cubicle type theory. That's amazing. We have got to embrace, welcome, and learn from these people because they have a lot to teach us. And the final point I want to make is that I think it's really great that there is a lot more attention being paid to matters of diversity, equity, and inclusion in the PL community these days. To really achieve this or address this in a way that addresses the bigger structural forces that exclude huge swaths of our population from academic and intellectual life, we have to go outside of our insular communities. We have to learn from the masses and from their needs. Interactive theorem proving does have the potential to bring mathematics to non-collegiate learners and informal students. And it also has the potential to bring those people into mathematics. But in order for this to be having a good impact, it has to be done in a way that meets their needs, a way that addresses their needs. And so I say, let's go down to the countryside and figure out what needs to be done. That's all I want to say. I just want to thank you all, and I really just hope that you have fun with the rest of the WITS. Thanks.
Yeah. Thank you for the great talk. It was very inspiring. Let's see. Richard, are there any questions in the room? Maybe I'll start with a question otherwise. I was wondering, maybe a bit controversial, but do we need all this higher dimensional stuff, right? I remember you also wrote a paper on XTT, which squashed down all the higher dimensional stuff, more or less. And yeah, there's something to be said for that being a very useful theory to do a lot of computer sciencey stuff, at least. So what's your current opinion on that?
Right. Yes. So I think that there is this usability gap between higher dimensional type theory and type theory that has stricter properties like proof of relevance and so on. It's kind of a funny thing that most of the motivations I gave for higher dimensional type theory are good properties of low dimensional type theory that higher dimensions automatically give you. So this maybe this makes one think there's something wrong here. So XTT was an attempt that Carlo and Julie, Daniel Gretzer, and I did to try and bring some of these high dimensional ideas into a low dimensional setting. And while we did some interesting stuff, I don't think the XTT type theory works very well. I think that there's a lot of both syntactic and semantic problems with it. On the other hand, there's a very interesting paper in Popple this year on something called TT ops, a variant of observational type theory. And the authors of this paper have proved the normalization theorem for it and argued convincingly that it satisfies a number of good properties. So I do think that there is definitely room for low dimensional solutions to these problems. The thing is that something like TT ops cannot have all the good properties that you want of low dimensional type theory. In particular, the interaction between propositions and types is not correct, mathematically speaking. And that's something that one may or may not care about. But in order to get the correct relationship between propositions and types, higher dimensional approaches seem to be needed, either that or just adding axioms to ordinary type theory that don't compute. So the higher dimensional stuff really helps if you're trying to have good semantic properties that also compute.
Right. Okay. Yeah. Thanks. Maybe. Oh, I see Richard has a question, but it seems you're muted, Richard, or at least I can't hear anything you're saying.
Can you hear me?
Now we can hear you. Yes.
Okay. Good.
Yeah.
Hi. Thanks for talk. So what's stopping us from using your technique of appending the side conditions to the local goals to do the same thing in ordinary actor as cubicle actor? Because it would be fantastic if we could see those side conditions as well and get rid of the yellow.
I think that's a very interesting and a good idea. I don't really know how to do it because I'm not an expert on unification. The yellow in AGA is coming from unification problems, and I don't know what would happen if you try to solve it in this way. One of the things about unification is that to make it work well, it's a global process because you're using information that comes from one unification goal and using it to solve another unification goal. So I don't know if you really can do it locally. So that would be really interesting to see if there is a middle ground, but I'm not sure what would happen.
Okay, maybe we'll.
Oh. What I think maybe we have one more. Do we have time for one more question here? Do you think?
Yeah, I see. There's also a few online questions now coming in, but yeah, maybe we can't do all of them.
Okay, so maybe do an online question, and then.
Okay, I see the most upvoted questions by Bas Spitters. He's asking if you could elaborate on your idea on algebraic hierarchies.
I don't have a lot to say. Basically, I think that we should ask the comrades working on SS Reflectant Hierarchy Builder what to do. Have a look at the papers on Matita, and then do it. I'm not an expert in this. I'm more of a user, and all I can say is that as a user, those tools have made me very happy. And I wish that it were easier to use stuff like that out of the box in the type theories that we have.
Right, yeah, okay. Makes sense. So I think then we'll move on to the next talk. But yeah, thank you again very much for agreeing to give the talk. It was amazing. I think I saw